Okay, it's 1 minute to. Hello and welcome to the first Earth to Earth seminar. Thank you for joining us today, 20th of August, 2020. Please visit our website, earth2earthseminar.com, for information about the series or to nominate a speaker. Earth to Earth is organized by a governing board with representation from UK universities, Nature Geoscience, and the British Geological Survey. But any UK institution that wishes to have a representative on the board should contact us by email. The email address is in the chat. It is our mission to engage the UK geosciences community with inspiring science from internationally leading researchers. We'll do this while promoting inclusivity and diversity, supporting the advancement of early career researchers, and highlighting geoscientists' contribution to addressing global environmental challenges. We'll be holding seminars every 2 weeks at this time and day. They're open to everyone. We can have 500 participants in the Zoom webinar, but there is also a live stream to YouTube. The lecture will be recorded and, with speaker permission, will be available on the YouTube channel with closed captioning. Our calendar, links, and further information are available on earth2earthseminar.com. During seminars, we ask that you follow our code of conduct, which you can find on the Earth to Earth webpage. For questions, please use the Q&A channel at the bottom of your Zoom window. These may be posted at any time during the seminar, and it should be possible to upvote questions that you like. We should have 10 minutes at the end of the seminar for me to relay your questions to the speakers. And now it's my pleasure to introduce today's co-speakers. We're very fortunate to have Raj Dasgupta and James Eguchi. Raj is a professor at Rice University in Texas and leads the experimental petrology group there. He's originally from India and has degrees from Javadpur University and the University of Minnesota. Among his major awards is the McElwain Medal of the American Geophysical Union. James is a NASA postdoctoral fellow at the University of California, Riverside. He did his undergraduate degree at UCLA and finished his PhD in 2019 at Rice University. Thank you very much for being with us, Raj and James, and please begin your seminar.
Thank you, Rich and Ollie, for organizing this wonderful concept online seminar series as the world deals with this awful pandemic. Hope whoever is listening to me, they're safe and healthy, and I will begin my talk praying for healthy life for everybody on this planet. So I will begin the talk with the title as it's up there on your screen. We'll talk about mantle melting, deep carbon cycle, and the rise of atmospheric oxygen for our planet. So probably one of the biggest questions that humanity is facing today is, are we alone in the universe? Especially as we continue to learn more and more about rocky bodies in our solar systems and beyond, the planets that we are naming as exoplanets. There is a growing need for us to understand what makes a rocky planet habitable. What are the key chemical ingredients we need at the surface of the rocky planets, and how those chemical ingredients are made available to generate and sustain life over long periods of the planet's history. So, of course, there are many types of rocky planets in the exoplanetary populations we are discovering. But of course, the planet we know the most is our own planet Earth. So if we want to look for an Earth 2.0, we may be looking for a planet with liquid water on the surface, meaning it has the right distance from the star, it has the right dose of greenhouse gases and in the atmosphere. And we may also be looking for an oxygen-rich atmosphere. But even our own planet may not have had these properties at the surface throughout its history. So more important queries might be that how through time, through various planetary and geologic processes, our own planet evolved to the current state, and how such evolutionary pathways may be different from other rocky bodies we will find through time. So two things, liquid water on the surface, oxygen-rich atmosphere. How do we get them? So of course, these are big questions. It requires an interdisciplinary endeavor. At RISE, we have launched such an interdisciplinary inquiry called Clever Planets to investigate conditions of chemical habitability of rocky planets. And Clever Planets stands for Cycles of Life Essential Volatile Elements in Rocky Planets. The web link for this project is up there on your screen. So what we are going to discuss today is simply a subset of large set of efforts as part of this big project. So as I just mentioned, in Clever Planets, we are trying to bring together astronomers, astrophysicists, earth and planetary scientists, which encompasses subdisciplinary expertise in petrology, high temperature geochemistry, geodynamics, fluid dynamics, low temperature geochemistry, atmospheric science, organic chemistry, and so on. And in terms of the tools, we are also including a large number of attempts, such as observations, theory, laboratory experiments in the fields of petrology, impacts processes, hydrothermal processes, geochemical analysis for, again, experimental samples, hydrothermal fractionation experiments, isotopic fingerprints, including dynamical climate modeling, geochemical modeling. So it's a large array of tools and expertise that really is making Clever Planets possible. James and my expertise are only, again, a subset of these. And what we will do in today's talk is to use disciplinary expertise in the field of petrology, high temperature geochemistry, a bit of geodynamics, and laboratory experiments in the fields of petrology and, again, geochemical modeling and geochemical analysis. So again, for us to understand chemical habitability of rocky planets, we truly need to understand the origin and maintenance of life essential elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, which I will be referring simply to as schnapps at rocky surfaces. So these availability and maintenance is basically a key step towards building a habitable world, right? Now, habitability, as you will have to, when you think about it, you'll have to recognize it's a four-dimensional concept. There are many planets that probably through its history at some point were habitable, but then planetary and stellar properties and processes may have taken such planet to an inhabited condition or inhabitable conditions. Whereas there may be other planets which started out with an inhabitable conditions early on, but again, through planetary and other processes have evolved to a habitable state. So the question is, habitability, as we think about it, it's a dynamic property, it's a four-dimensional concept. How do we think about it as we want to evaluate the availability of schnapps at rocky surfaces? So because of this time dimension, I think it's extremely important for us to track life essential elements through whole planet scale processes, not just thinking about the availability of them at the surface, but availability and their fluxes and distributions through whole planet. And I will just exemplify that through a simple example of carbon cycle here. So to the left of your screen, what you are looking at is a textbook example of short-term carbon cycle or surficial carbon cycle, where carbon is exchanged between near surface reservoirs such as hydrosphere, atmosphere, biosphere, and so on. And in this type of time scale, in this type of carbon cycle, the reason it's called short-term carbon cycle, here the fluxes are short, but more importantly, the reservoirs of carbon in any of these near surface systems are only 10 to the power 17 grams in each reservoir. But if you compare that with the deep carbon cycle, which is the diagram or one of the estimates of that deep carbon cycle to your right, here the fluxes may be similar, 10 to the power 13, 10 to the power 14 grams of carbon per year, but the reservoirs that we are dealing with are much, much larger, orders of magnitude larger, almost like 5 to 6 orders of magnitude larger, 10 to the power 23 grams of carbon or so. So this comparative look at deep carbon cycle versus short-term surficial carbon cycle would immediately tell us that the long-term surface availability of carbon on Earth can only happen by the permission of the mantle. Without these deep fluxes, maintenance of at least carbon in our surface would not have been possible. So as far as providing carbon to the atmospheric reservoirs or near surface reservoirs for a tectonically or volcanically active planet, volcanoes would be the obvious place to start. These are the places where carbon would be spewed out from the interior of the reservoir, interior of the planet, and would be provided to the near surface reservoir. For a tectonically active planet such as ours, we of course have process of recycling and subduction of putting carbon or other elements back into the planet. But as far as the outflux is concerned, volcanoes are the right place to start. So volcanism is responsible for creating atmosphere in a long-lived volcanically active planet, thereby influencing the budgets of greenhouse gases. That means it's critical for maintaining liquid water on the surface. It is also the process that supplies these life essential elements. However, again, volcanoes are just simply surface expressions of mantle melting processes. So although this outgassing is the thing we observe or readily recognize, the main thing we should be paying attention to is the mantle melting process or partial melting process in the interior of our planet, which makes an element like carbon available to the magma to begin with. Okay, so for an active planet like ours, mantle melting process, this is like textbook examples, typically happens by adiabatic ascent of solid rocks, which crosses the solidus. Partial melts, silicate partial melts are produced, and carbon partitions into that silicate partial melts, which eventually decompresses and releases carbon-bearing fluids to the surface. So the question is, how through this mantle melting process, carbon is made available to the melt, which eventually degasses or releases its fluid and gives up to the surface. Carbon is basically just like any other trace elements in some ways. It's present in the mantle for our own planet only in tens to hundreds of parts per million in concentration. So it's actually very minor, but again, remember, mantle is a huge reservoir. Concentration may be low, but the total budget is very high, right? Because of its low solubility in mantle silicates, unlike most other trace elements you may have heard of, carbon is actually, in that sense, not a normal trace element. It's a special trace element. Why? Because it is not incorporated in the mantle silicates. So it doesn't really partition in the same way as we think of partitioning of trace elements during mantle melting. It is actually present, although present only in that low concentration, it is present in various accessory phases in the mantle. So to the left of your screen, these are some of the common accessory carbon-bearing minerals that are known to be present at the shallow to mid upper mantle depths of our planet, like dolomite, like calcite, magnesite, and maybe graphite and diamond. And the diagram to your right is basically showing you how, as a function of effective partial pressure of oxygen on the x-axis and depth on y-axis, the stable accessory phase of carbon is expected to vary. At relatively high oxygen fugacity, meaning when conditions are oxidizing, we expect carbonate to be stable. When you go to relatively reducing conditions, you expect graphite or diamond at greater depths to be present. So interesting thing about carbon is, again, it's stored in accessory phases, but it can also exist in multivalent state in different storage mechanism. And that, as I would establish, is a key element of understanding carbon's behavior during mantle melting. So what do we know about carbon's behavior during mantle melting? It's based on the modern world behavior of an oxidized upper mantle on Earth today. And the key aspect of that is the fact that in the absence of any volatiles or carbon, the solidus of the mantle is shown with this red line here on this plot of temperature versus depth. And in the presence of carbon, when trace amount of CO2 is present in the mantle in the form of carbonates, that solidus is depressed immensely by order of 400, 500 degrees at any given depth. So because of that, during that adiabatic descent of mantle parcel, mantle melting can commence at much, much deeper depths than otherwise it would be possible. And that melting process generates extremely CO2-rich mantle melts. There are different names that people give, like carbonatite, kimberlites. The bottom line is these are sort of very, very CO2-rich melts, or carbonated silicate melts, sometime I would call them. And these low-degree melts are generated very deep. As a consequence, per unit geologic time, large volumes of mantle can be processed through time. So outgassing efficiency can be very high because large parcels of the mantle is participating in this melting process. However, things will change if the mantle is not oxidized at depths. So for example, I may not have pointed out, for our own planet, it is expected, especially for mantle domains beneath continents, that as you go deeper and deeper, the oxygen fugacity is actually dropping, meaning the system is effectively behaving in a more reduced way as you go deeper. If that is the case, if mantle is not oxidized at depths for our own planet, the solidus that I showed you, that carbonated peridotite solidus that was very, very depressed, may not remain so depressed like this. It actually can be almost effectively back to that behavior of carbon absent melting conditions. So if that happens, if mantle is reduced, there may not be any deep melting. Okay, so that large volume processing will be truncated if mantle is reduced. Of course, this is the behavior of our present day Earth, where there may be a gradient in oxygen fugacity with depth, and in different domains of our planet, you may be expecting this deep carbonated melting somewhere, and maybe not so deep carbonated melting elsewhere. But there is a more interesting thing is, if we take a comparative planetology approach, there may be difference in oxygen fugacity or oxygen partial pressure in the mantle of different planets completely, meaning not just its gradient with depth, but even at any depth, some other planets may be much more reduced and have that graphite and diamond present rather than carbonate present, right? So the figure to your left shows a scenario where carbonate is present throughout, and the diagram to your right shows a scenario where carbon is present not as carbonate, not as this oxidized form, but as this reduced form such as graphite or diamond. So the key difference is, in the left, you will expect that deep carbonated mantle solidus to be relevant, and deep CO2 rich melts will be generated, and large volumes of the mantle will be processed through this solidus, and lots of melts will be created. Whereas, and large volumes will be degassing. Whereas the diagram to the right shows that deep carbonated mantle solidus is irrelevant there, because carbonate cannot impart that control on the solidus because carbon is present as graphite. So the solidus, where the melting first begins as a function of upwelling, is actually much shallower. It's effectively that volatile free peridotite solidus. So in that case, the reduced mantle, the melting happens very shallow, only basaltic melt is generated, and lesser mantle volume is processed per unit geologic time, right? So of course, there is this control of going from oxidized to reduced state of carbon, that the mantle volume processing can be drastically changed as you go from oxidized to reduced. But now we need to understand that, okay, even if, let's say, the mantle is reduced and graphite is present and mantle is melting relatively shallow, how much carbon can actually degas even through that type of a melting process? In graphite or diamond-bearing mantle, carbon release via magmagenesis relies then on a two-step process, because in this case, you are not generating that CO2-rich melt. You are generating a normal silicate garden variety basaltic melt that we observe, for example, in mutationic ridge basalt systems and so on. In that type of systems, because mantle contains graphite, that graphite first needs to be oxidized to effectively think of generation of a CO2-rich fluid, and that CO2-rich fluid then will bond with oxygen in the melt to get dissolved as carbonate anion in the melt. In case of mafic melts, it could be molecular CO2 for other types of melts. So because of that, because of this nature of the reactions, you can imagine if the oxygen fugacity is low, the graphite oxidation is expected to be less and less. As a consequence, the CO2 dissolution in the silicate melt is expected to diminish as a function of decreasing effective oxygen partial pressure or oxygen fugacity. So shown in this plot from James's work is CO2 concentration dissolved in graphite saturated mafic basaltic melt as a function of oxygen fugacity. This is, again, these are petrologic terms, so don't have to worry too much about it. All you need to know is that as you go to the left, this is more and more reduced. As you go to the right, it's more and more oxidized. If you are to the right of this dashed line, you may have CO2-rich vapor present. If you are to the left of this line, CO2 cannot exist and in that oxidized form, and the stable form of carbon is graphite or diamond, in this case, graphite. So the point is, the primary melt will dissolve less and less carbon if mantle is more and more reduced. And indeed, that was a thermodynamic prediction, but indeed, when we do a lot of laboratory experiments at various pressures and temperatures using different types of silicate melt compositions, we do observe that systematics. In other words, with decreasing oxygen fugacity, all these points are experimental melt compositions that are saturated with graphite, and all it is telling you how much carbon silicate melt can dissolve at graphite saturation. And as you can see, with decreasing oxygen fugacity, carbon dissolution becomes less and less efficient in silicate melt. The only difference is that if the hydrogen fugacity is high, or if your melt is very hydrous, there is a possibility of dissolving a little more carbon, because at that type of conditions, sort of CH speciation or methane dissolution can start to become important, as shown with this reaction. But broadly speaking, for nominally anhydrous type of magma, as you go to more and more reduced conditions, you should expect less and less carbon dissolution. So what does that mean when we think about different planets that may be at drastically different FO2 states? And so this is a compilation of our estimates of oxygen fugacity of planetary interiors or rocky reservoirs of different solar system materials. And this is again shown in that sort of delta IW scale, again, more oxidized to the right, less oxidized to the left. And what you can see is, other than our own planet, which may have a range of oxygen fugacity depending on depths and so on, most other, or pretty much all other known solar system reservoirs, such as planets like Mars, the Moon, Mercury, parent bodies of various meteorites, achondrites and chondrites, are expected to be graphite saturated rather than carbonate saturated, right? So the question is then, what sort of carbon degassing efficiency we would expect from these type of bodies that are much more reduced? So this is an example calculations to get to that point. What I show here is, as a function of mantle oxygen fugacity, again in that Arrhenius type buffer. So again, CO2 vapor saturation to the right, meaning very oxidized, graphite saturation to the left, and getting more and more reduced. I am calculating the carbon content of mantle-derived primary or primitive partial melt for different types of bodies, such as Mercury, Moon, Mars, and Earth. And as you can see, and remember, this is a log scale on y-axis. So as you go to, and also log scale on x-axis, as you go to extremely reducing conditions, the primary carbon that is available in partial melts in reduced bodies is much, much, much lower, orders of magnitude lower, right? So planetary mantle would release vastly different carbon contents via production of primary melts if the oxygen fugacity or partial pressure, effective partial pressure of the planetary interiors vary quite a bit. And that's what we are pointing out here. So what did we learn so far? Any lessons, anything to remember from this talk? Is degassing efficiency of carbon from a rocky interior depends heavily on the redox state of carbon, meaning that storage mechanism. Is it graphite or diamond? Is it carbonate or CO2? More reduced the condition is, less degassing is expected. Again, but the important point is that less degassing is kind of contributed by two factors. One is, of course, the lower solubility of carbon in mantle melts as it is produced at graphite or diamond saturation. The other factor is much less volume of mantle would be processed through that solidus, through that magma generation process over planetary history, because the solidus will not be as depressed as it would be in the presence of an oxidized mantle. So far, I have talked about carbon cycling, and we can see that that carbon is extremely important in terms of a life essential element, its supply to the surface, its importance as a greenhouse gas. But in this slide, what I'm pointing out, that carbon is not important just for its own evolutionary history. It's actually tied to oxygen through this simple photosynthesis reaction where CO2 and water reacts to form simple organic molecule and produces oxygen in the process. So the evolution of CO2 in the atmosphere and oxygen in the atmosphere, they are intimately linked. So the question for us, for our own planetary history, as we look at it, if we look at our best estimate of oxygen evolution in the atmosphere of our planet through the history of our planet, there is known to be this great oxygenation or great oxidation event at around 2.4 billion years ago, and then maybe a lull and then again increase later on. So how did that oxygen increase actually take place, and whether or not it actually happened through the widely accepted argument of simple burial of organic carbon, production of cyanobacteria very early on, but eventual burial of that organic carbon. But the question we are going to ask here, because we are taking this whole planet scale approach, is simple burial of organic carbon in the sedimentary reservoir sufficient to produce oxygen and sustain that level of oxygen? As it turns out, there are some arguments that when the hydrothermal activity was probably higher in the past with hotter mantle potential temperature and so on, just burying organic carbon at the near surface reservoirs may not be sufficient, because there may be thermal events that would break down that organic carbon in the sedimentary reservoirs and release that organic carbon back into the atmospheric systems again. And then that would not be the favorable process to maintain that elevated oxygen that took place after GOE, or Great Oxidation Event. So we started asking these questions a few years ago, that not only just burial, but what really controls the efficiency of organic carbon subduction. Why did we start thinking about subduction? Is because this would be like a real good burial mechanism, not just burial in the sedimentary reservoirs, but truly sequestering into the mantle for much longer time scale. And that, we thought, would be a good way to sustain that elevated level of oxygen after GOE. So organic carbon in sediments, turns out that it undergoes graphitization during diagenesis and low-grade metamorphism. So what I was pointing out in the earlier part of my talk about the behavior of graphite in a silicate rock, some of those lessons can be transported even in this problem, because what we are going to look at is behavior of a crustal rock as it subducts, meaning as it heats up and as it undergoes metamorphism and potentially partial melting at higher pressure. What is the behavior of that graphite in that sort of sedimentary systems? So the chief agent that can mobilize organic carbon when organic carbon is graphitized in hotter subduction zones of the past, such as what we may be expecting in the Archean, would be production of hydrous crustal melts from the slab, from the downgoing sediments or downgoing oceanic crust, and how much carbon can be mobilized through that partial melting process. And we thought that would be a key hook for linking this observation to GOE. So this is a study that one of the former students of mine, Megan Duncan, who is now an assistant professor at Virginia Tech, did as part of her thesis. What she did is laboratory experiments at sort of subduction zone type of conditions. Pressure, temperatures are listed up here for a hydrous melt that is very silicic. So typically the type of melts we would expect to be produced through fluid present melting of subducted oceanic crust or sediments. What we were trying to do is to figure out how much CO2 dissolution can take place in this type of melts in the presence of organic carbon. Or of course, we are substituting organic carbon as graphite, because we made that assumption that graphitization process is relatively efficient and happens early during diagenesis or metamorphism. We then took these experimental products, which are basically nice homogeneous glasses without any fluids again, because it's only stable, it's only saturated with graphite, not CO2-rich vapor. And we wanted to figure out how much CO2 dissolves in these glasses, because that would tell us the recycling efficiency or mobilization efficiency of carbon when subducting sediments are organic carbon saturated. We did microprobe analysis, we did FTIR and SIMS to figure out dissolution mechanism and total carbon content in these glasses. So this is just somewhat of a technical slide, I suppose, but just showing you that we did Fourier transformed infrared spectroscopy to figure out both the total CO2 content dissolved in these partial melts, silicic partial melts produced during subductions, as well as the dissolution mechanism of carbon. What we find that there is both CO2-rich vapor phase that's stable, that dissolves in the silicate melt, and there is also carbonate melt, a carbonate species that dissolves in silicate melt. So when we need to figure out the total amount of carbon dissolution and mobility through this type of melt production, we need to pretty much create a thermodynamic framework that can deal with both molecular CO2 dissolution in hydrosilicate melt as well as carbonate anion dissolution in hydrosilicate melt. We need to combine the two. So that's what we did. We put our experimental data in a thermodynamic framework so that we can figure out how, as a function of pressure and temperature, for that type of hydrosilicic melts, CO2 dissolution would vary, and also as a function of oxygen fugacity, because remember, again, at graphite saturation, all this dissolution mechanism of CO2 in silicate melts are tied to that graphite oxidation mechanism, as I pointed out earlier for that another context. So that's what we did. Then we had some estimates of how slab surface temperatures may have varied through time. Of course, it's a big unknown. We made assumptions there. We made the assumption that it may be tied to mantle potential temperature evolution through time, and there may be some sort of a geologic evolution of slab surface temperatures. So we can calculate then as a function of cooling of our planet, evolution of the slab surface, and so on, how as a function of pressure and temperature, and oxygen fugacity at graphite saturation, rhyolitic slab partial mills can dissolve CO2. Okay. Once we did that, we then can calculate, right, as a function of pressure and temperature. So these are some estimates of slab pressure, temperature, depth trajectory for modern slabs that have a range and ancient slabs that we assumed in that particular study by Megan that it could have been hotter. And we can now calculate as the slab passes through as a function of depth, what type of CO2 can be mobilized or carbon can be mobilized at graphite saturation through that type of crustal melt production. And that's what is shown here to the panel on the right. CO2 content as a function of depth following that slab PT trajectory. So of course, as you get hotter, you can mobilize more carbon. As it is cooler, you would mobilize less carbon. But the point is, even at hotter conditions, the mobilization of carbon, because it is reduced system, because it's organic carbon present system, mobilization of carbon is not so much less than what we would expect in carbonate, which probably James would tell you much more about. So what we did in this study then is to link our experimental observation of the efficiency of carbon dissolution in hydrosilicate melt at graphite saturation at this reducing condition when these crustal melts were produced, and linked it to some models or assumptions of subduction history of our planet, again, which is a hotly debated topic, and showed in that particular study that it is possible to model that rough order of magnitude estimates that we have for rise of oxygen in the atmosphere. Because what we are doing is we are taking this reaction, we are producing organic molecules, which is eventually graphitized. That graphite is then subducted deep, and we are calculating that subduction efficiency based on how much is mobilized in the subduction zone. So the amount that is not mobilized by CO2 dissolution in hydrous melt, the remaining is actually subducted deeper, because we are calculating that subduction efficiency through our model calculations, through the thermodynamic constraints we got in terms of carbon mobilization silicate melt. We can calculate that subduction efficiency. And when we do that, we can get this complementary part, meaning we can calculate what the rise of oxygen would be, right? And in this 2017 study, Megan and I tried to convince the readers that yes, it is indeed possible if we have the right tuning of the start of subduction through this organic carbon subduction to produce this great oxygenation event. But there are lots of surface geochemistry for our planet that also needs to be checked when we really want to understand this rise of oxygen around GOE, not just this carbon subduction, because in this model, it was tied very much to the timing of subduction initiation and the efficiency of subduction and so on. So what James is going to talk about after me right now is a more complete picture of that, and how should we be thinking about not just the carbon geochemistry at the surface, but as well as this rise of oxygen. So I will hand it over to James. James, it's all yours.
Okay, thanks, Raj, and thanks for kind of setting up this portion of the talk that I'm going to go into now. And so if you could go to the next slide. Are you guys able to hear me? Okay. All right, thanks. Okay. So now that Raj has kind of highlighted how carbon behaves differently under different redox conditions, I wanted to kind of share about how these differences may have played a role in the evolution of atmospheric oxygen, as well as the carbon isotope record here on Earth. And so as Raj discussed earlier, around 2.5 billion years ago, there's thought to be this dramatic rise in oxygen, known as the Great Oxidation Event. And seemingly coincident with this rise in oxygen is the Lomaguni event, which is a large, long-lived positive carbon isotope excursion, which we can see in this bottom panel. And one of the traditional views on the connection between these two events is the increase in F-org, or just the fraction of carbon buried as organic carbon relative to inorganic carbonate. So when F-org increases, oxygen accumulates due to the barrel of more organic carbon, and the delta 13C of marine carbonates increases because organic carbon prefers to take up carbon 12. So if more organic carbon is buried, the reservoir from which carbonates is forming becomes enriched in carbon 13, leading to a positive carbon isotope excursion. And if we could go to the next slide, please. However, studies have suggested that the rise of oxygen may have actually preceded the positive carbon isotope excursion of the Loma-Gundi event. So here in this figure, the black curve is showing the delta 13C of marine carbonates through time. And the red symbols are showing this value called cat delta 33S, which is, we can think of as being sensitive to atmospheric oxygen. So when oxygen is low enough, photochemical reactions can cause sulfur isotopes to fractionate in a mass-independent fashion, resulting in non-zero values. However, once oxygen rises high enough, those photochemical reactions can no longer proceed, and there's no longer mass-independent fractionation of sulfur, resulting in these cat delta 33S values of 0. And so when we look at these two records, they suggest that oxygen may have actually begun to rise before the onset of the carbon isotope excursion of the Loma-Gundi. And therefore, if the Great Oxidation Event and the Loma-Gundi were indeed temporally disparate, it becomes difficult to explain both of these events by increased F-org. And additionally, from mass balance considerations, looking at the magnitude of the carbon isotope excursion, the Loma-Gundi may have released around 20 times present-day oxygen levels, which is unlikely according to the geologic record. So therefore, if F-org doesn't link these two events, it becomes kind of important to think of other possible explanations to explain these two phenomena. And so for this portion of my talk, I want to talk about how the recycling of carbonates versus graphitized organic carbon in the mantle may provide a way to link the GOE and Loma-Gundi events, while also remaining consistent with this puzzling timings between the two events. So if you go to the next slide. So I wanted to kind of briefly talk about what is thought to control these burial fluxes of carbon. So the production flux of both carbonates and organic carbon are controlled by elements such as calcium, magnesium, and phosphorus, which are delivered to the ocean via continental weathering. And this weathering flux is thought to be controlled by atmospheric CO2 concentrations, where higher CO2 leads to higher temperatures and higher precipitation, leading to higher fluxes of silicate weathering. Therefore, an event which increases CO2 could lead to the increased burial of both carbonates as well as organic carbon. And thus, increase in CO2 emissions could lead to increased burial of both organic carbon as well as carbonates, which would lead to a rise in oxygen. And importantly, if the burial flux of both organic carbon and carbonates increases proportionately, we can get oxygen to rise without this simultaneous change in the carbon isotope values of marine carbonates. And if we could go to the next slide. So then it becomes important to look at if there's any reasons to believe that CO2 emissions might have increased around the time of the GOE and Loma-Gundi. And what I'm showing here in this figure is the zircon record through time. And although it's still very highly debated, some researchers have proposed that this zircon record suggests around 3.0 to 2.5 billion years ago, there may have been some transition in the tectonics, the tectonic activity on Earth. And one of the propositions is that there was some transition from something like more of a stagnant lid to something more of the fully developed plate tectonics that we see today. And if there was such a transition, the initiation of long mid-ocean ridges and arcs could have led to a rise in CO2 emissions, which could have led to increased weathering and increased carbon burial. And if the F-org doesn't drastically change, then we could have oxygen rising without this simultaneous change in the carbon isotope record of marine carbonates. And so for the rest of my portion of the talk, I'll be talking about how the carbon cycling in the mantle could have driven this delayed positive carbon isotope excursion. And so if we go to the next slide, please. And so after this increased flux of carbon is buried on the seafloor as carbonates and organic carbon, they're going to be subducted into the mantle, during which organic carbon is going to metamorphose to graphite. And as Raj was talking about earlier, these two different forms of carbon are going to behave differently once they're subducted into the mantle. So if we go to the next slide, please. So on the left figure, I'm showing the PT path of a subducting slab compared to the melting out boundary of carbonates. And on the right figure, I'm showing the percentage of originally subducted carbon that's going to remain in the slab as it subducts down up to higher pressures. So we can see as once the slab goes past the melting out boundary of carbonate, virtually all carbonate hosted carbon is going to be released from the slab. If we go to the next slide, please. So these blue lines are contoured for the weight percent of carbon that can be hosted in carbonate in response to metamorphic decarbonation, which is just another way to release carbon from the subducting slab. And this right panel shows that significant amounts of carbon can also be lost upon subduction due to the metamorphic decarbonation of carbonate. And so if we go to next slide, please. In comparison, in the black curve, I'm showing how much carbon is going to be retained in the slab in the form of graphite during the melting of this slab. And this figure shows that while carbonates are likely to be efficiently released from the slab, graphitized organic carbon is likely to remain in the slab and be subducted beyond subarc depths. If we go to the next slide, please. So if carbonates are being preferentially released from the slab relative to organic carbon, then we might expect the CO2 emitted at arcs to have a heavy delta 13C. And what I'm showing here on the left is a figure of a global compilation of delta 13C of CO2 emissions at arcs. And this study showed that arcs are on average heavier than the canonical mantle value of around -5, which is thought to be the kind of canonical value of CO2 emitted at mid-ocean ridges and kind of the value of the ambient mantle. And this kind of heavy value observed at arcs could suggest that these arcs are possibly emitting CO2 that's preferentially sourced by carbonate-derived CO2. And so if we go to the next slide, please. And so then another important question is to kind of think about whether this carbonate-derived signature is coming from the slab or the upper crust, which this arc magma can kind of pass through. Because if it's coming from the crust, then it's not really telling us about what's being subducted. And so what I'm showing here is a plot of the delta 13C of the CO2 emitted at a particular arc versus the F org of the sediments entering that the trench feeding that arc. And so what we can see is that the data shows that as these sediments become more organic rich, the delta 13C of those arc emissions actually become more negative, suggesting that the subducting sediments are playing a significant role in kind of controlling the delta 13C of the CO2 being emitted at different arcs. And I just want to point out that the two orange data points are that kind of lie off this kind of negative trend are arcs that are being erupted through carbonate terrains. So this could possibly explain the shift of those data points up to higher values. And also on this figure, there's this dashed line. And this dashed line is just a mixing line between 0% organic carbon at 0 per mil and 100% carbon at organic carbon at -25 per mil. And along this mixing lines are the values that we would expect if the sediments with a particular F org are releasing carbonates and organic carbon with equal efficiency. And the fact that a lot of these data points are plotting to the above and to the right of this line is suggesting that carbonates are likely being released preferentially relative to organic carbon at these arcs. And if we go to the next slide. And so now that perhaps carbonates have kind of been stripped off in this subarc region, we want to see if there's any evidence that organic carbon is actually being subducted deep into the mantle. And one way to kind of look at this idea is to look at the carbon isotopes of diamonds, which is kind of shown here in this figure. And one of the first things to note is that peridotite diamonds are tightly clustered around the canonical mantle value of around -5 per mil, while eclogitic diamonds have this tail off to more negative values, possibly suggesting that subducted oceanic crust is kind of retaining some of this organic carbon. Additionally, if we look at lower mantle and transition zone diamonds, they do have populations with delta 13C values very close to organic carbon. which could suggest that organic carbon may be subducted deep into the mantle. So now if we have this subducted oceanic crust being enriched in organic carbon, and this mantle becomes entrained in upwelling mantle plumes, we might expect that these plume-fed volcanoes are emitting CO2 with light carbon isotopes. So we go to the next slide, please. And what I'm showing here is a compilation of carbon isotope measurements made on samples from different ocean islands compared to mid-ocean ridges and arcs. And one thing that is important to point out for this figure is that samples from Coolau, Society, Luihi, and Pitcairn are made on glasses, which are subject to isotope fractionation upon degassing. And so importantly, I want to point out that marked with these green stars are the least degassed samples, so they might be the most representative of the carbon isotope signature of those ocean islands. And also, I want to point out that the measurements made at Kilauea were made on high temperature gases, which would be the most comparable to the ARC data set. And when we look at this compilation, it suggests that possibly some ocean islands could be emitting CO2 with a light delta 13C, possibly caused by the enrichment of organic carbon in these settings. So if we go to the next slide, please. So then if we are proposing that the Loma Gundi is a result of preferential release of carbonates at arcs and the preferential release of organic carbon at ocean island basalts, then the duration of the Loma Gundi event would be controlled by the residence time of organic carbon in the mantle. And when we look at the record, the Loma Gundi event is around 200 to 300 million years. And I don't know if this is going to work, but this is like a little video on this slide, Raj. It seems to be kind of plain. And so in this study, the researchers were interested in whether the subducted slab spends a lot of time kind of stagnating in the lower mantle. And what they concluded is that oceanic crust doesn't really spend a significant time stagnating at the core mantle boundary. So therefore, this time scale is kind of, we can think of it as the oceanic crust traveling this kind of symmetric cell down to the core mantle boundary horizontally and then back up. And this travel distance would be around 10,000 kilometers. And if this slab is traveling at 1 to 10 centimeters per year, then that time scale would be 1 billion years to 100 million years, which would kind of put it on the same time scale as the Loma Gundi event. And so now if we go to the next slide. Here's just the kind of schematic figure of the proposed mechanism that we're using to describe the GOE in Loma Gundi. And so this mechanism is just kind of stating that increased CO2 emissions could lead to increased carbon burial, and the deep recycling of this carbon could lead to the carbon isotope excursion of the Loma Gundi. And so on this figure, I'm just showing some of the important assumptions that we use to build up this simple box model to explain the GOE and Loma Gundi. And first, I want to point out that the burial flux of carbon is controlled by the concentration of CO2 in the ocean atmosphere system. And second, throughout the model evolution, we keep F forward constant at 0.2. Third, atmospheric oxygen is proportional to the mass of organic carbon in all Earth reservoirs. And fourth, mid-ocean ridges always release CO2 with -5 per mil. Arcs are releasing CO2 with carbon isotopes controlled by subducted carbonates, and ocean islands are releasing CO2 with carbon isotopes controlled by subducted organic carbon. Fifth, we're assuming that subducted carbonates are released at arcs on the order of 10 million years after subduction, while subducted organic carbon is released at ocean islands on the order of 100 million years after subduction. If we go to the next slide, I'll kind of walk through some of the model results. And the first panel, we're just going to be showing delta 13C of marine carbonates with the data points showing compilation of some of these measurements. The second panel is showing the evolution of atmospheric oxygen through time, with these blue regions kind of showing the estimates of how we think oxygen was evolving through time. And on the third panel, it's going to be showing the carbon fluxes at different volcanic settings, as well as weathering fluxes. So if we go to the next slide, please. So we have all the model evolution and perturbations in this model are kind of driven by CO2 fluxes shown in this third panel. And if we go to the next slide, please. At around 2.5 billion years ago, we prescribed an increase in CO2 emission at mid-ocean ridges, which is shown by this orange curve. And as a result, the weathering fluxes increases, leading to increased carbon burial, as well as increased oxygen shown in the middle panel. And shortly after this increase of carbon burial, the arc flux responds to this increased carbon subduction flux, kind of shown in this blue curve. And this, the result of increased arc fluxes is shown, you can kind of see it in the top panel with increasing carbon isotopes recorded in marine carbonates. And I just wanted to put in this vertical dash line to emphasize that in this model, we can get oxygen to rise prior to the positive carbon isotope excursion, kind of consistent with GOE and Loma-Gundi. And if we go to the next slide, then after about 300 million years, the ocean island CO2 flux responds to this increased subduction of carbon, releasing this CO2 with a light carbon isotope, kind of ending the positive carbon isotope excursion. And if we go to the next slide. So just kind of a conclusion for my portion of the talk is that the GOE and Loma-Gundi may have been driven by increased CO2 emissions and the differing cycling behavior of carbonates and organic carbon in the mantle. And this different behavior of carbonates and graphitized organic carbon may lead to carbon isotopes varying systematically at different volcanic settings. And this mechanism also provides an alternative explanation for driving long-lived positive carbon isotope excursions without changing F-org at all. And I think I'll turn it back over to Raj now.
Thank you, James. That's perfect timing-wise. So I'll just wrap up with a couple of things, I believe. If I can move my slide again. Yeah. So what we probably learned as potential lessons or take-home messages from James's portion of the talk is our planet's surface oxygenation may be linked to deep carbon cycle. And in the differential behavior of organic or reduced carbon versus carbonates, which is oxidized during subduction, is basically a key element in this phenomenon we are proposing. And as a consequence, what we would argue that Earth's surface geochemistry for carbon and its temporal relation to rise of oxygen and its evolution in our planet's atmosphere, they are consistent with the deep carbon cycle geodynamics. And one thing to point out in both James's presentation and what I spoke to you guys about earlier, the dichotomy or the differential behavior of reduced versus oxidized carbon in magmatic processes is the key. Either it's crustal process or crustal processing in subduction zones or magmagenesis in the upper mantle. This different behavior of oxidized versus reduced carbon is what's driving pretty much both parts of our talk, or key elements in both parts of our talk. So as closing thoughts, what I think, if you set aside the specific arguments we made for our different parts of our stories, what we are basically saying is that surface and atmospheric processes and properties are closely related and linked to mantle processes and properties, especially when we think about planetary habitability over long time scales. So what we are suggesting, are we suggesting that Earth's history is telling us something critical for a planet to be tectonically active and volcanically active, for it to be habitable or chemically habitable? That's what basically what James argued would suggest. Or for a planet to have complex life forms or rich oxygen bearing atmosphere, does it need to be again tectonically and volcanically active? That's again what we have suggested. We do not know really the answer to this question, although our look at our own planet's evolution and the papers we have written based on these would suggest so. But it's important to keep in mind, we have only one planet that we have known so far that is inhabited. So a lot of lessons need to be learned by studying our own planet's evolutionary history as we march along, exploring and discovering new worlds that potentially may be habitable, or we may find even evidence of life at some point. With that, I will end and acknowledge funding from different funding agencies such as NASA and National Science Foundation in the US, as well as support from Rice University. And I'm pointing out our website, cleverplanets.org, and you can follow us on Twitter at clever_planets. We are looking for interested postdocs and students always who might be interested in exploring various aspects of surface interior interactions through petrological and geochemical studies. With that, I'll stop. Thank you.
Thank you very much, Raj and James, for the excellent talk. It is a sad truth about the COVID age and Zoom seminars that you can't hear all the applause of the audience, but I'm sure that there is a lot of applause out there, and some of it is coming from right here. I want to ask you some of the questions that have been posted in the Q&A. They haven't really.
I can also see them. If
okay.
you.
Do you want to choose one, or should I read to you what I have?
Okay, if you want to select them, if there are many, go ahead.
There's one from the beginning of the talk that was up early. What do you think sets how oxidizing a planetary mantle is in the first place, and then goes on and influences how carbon is processed over the planet over its history?
Yeah, that's an excellent question. That's also another part we try to explore in our group or investigate that we didn't talk about in this particular presentation. There are multiple processes that can set the oxidizing conditions of the interior. Of course, there could be distinctions in the planetary mantles or planetary like accreting materials as a function of heliocentric distances, as we know from our own solar system, how oxidized or how reduced different accreting planetesimals and planetary embryos could be. That can vary. You can have more oxidizing materials from outer part of the solar system, more reducing materials from the inner part of the solar system. So as you are building planets with more and more materials from, let's say, inner part of the solar system, as we know from our own solar systems, your planetary mantles may be more reduced that way. Of course, that's the first step, accretion. But then there is also an important part of metal silicate differentiation and the size of the body. And that metal silicate differentiation can also set what will be the remaining FeO content in your silicate reservoirs, and accordingly, what would be the oxygen fugacity. So for example, we think for Mars, such metal silicate differentiation took place at a slightly more oxidizing conditions than the average condition of metal silicate equilibration for our planet. As a consequence, Martian mantle is thought to have more FeO in the mantle than we have in our planet's mantle, for example. But then there could be other processes such as volatile degassing, like hydrogen degassing and hydrogen escape, that can also influence the oxygen fugacity of the planetary mantle. So there is probably not one answer that would explain potential range or differences that we see in our own solar systems. There are probably a multitude of processes.
Another question from the audience. James, what allows the lag between PO2 rise and the delta 13C response?
Okay, yeah, I think I must have brushed over that, but that's a good question because it's important to the kind of story. And the reason for this lag is because oxygen is going to rise as soon as the increased flux of organic carbon is buried on the seafloor, while this delta 13C excursion is going to occur until this increased flux of carbon is deposited on the seafloor, subducted into the mantle, released from the slab, and then emitted at the arc volcano. So there's that kind of imposes this time delay between the rise of oxygen and the carbon isotope excursion.
Thank you. I'm going to try to squeeze in one more from John Blundy because I'm interested here. The modeling seems to assume that there's no carbon isotope fractionation during any of the decarbonation processes that occur during subduction. Is that correct? And if so, how well established is the absence of any carbon isotope fractionation under the relevant conditions?
Yeah, so in the model, the way the equations are set up, we're not building in any isotope fractionation during this decarbonation process. But one important thing that we're, I guess, building into this model is kind of full decarbonation of carbonates at arcs and full decarbonation of this organic carbon at ocean islands. And so if we have basically the entire carbon reservoir from one form moving into being degassed or decarbonated at some particular process, then just due to this complete reaction, we're not going to have any carbon isotope fractionations is what we're building in. But I'm sure that that's just an assumption in the model, and it's something that we can kind of explore further. And I think it would be important to do to see how it affects the results.
Great. All right. You know, there's never enough time to really dig into the discussion that comes out of a seminar like that. The YouTube channel may have the option to have some discussion, and anyone's welcome to go to the YouTube channel, watch the talk, and leave comments, I think. So I want to thank the speakers once again, Raj and James, for taking the time in very different time zones from the UK to give us this really interesting talk. And to everyone who came to the first Earth to Earth seminar, I want to say thank you to you, and we hope to see you again. And we appreciate the support of this initiative.
Yeah, thank you for organizing, and thanks for tuning in, everybody.
Yep. Thank you. Thank you to the organizers, and thanks for joining. Stay safe.